Hey everyone, this is the homework help video for homework number 6, discrete random variables. Let's just jump straight into it. So the first problem on the assignment is our first group of problems is 13 through 17. So let's go look at those. Where'd my window go? 13 through 17. So those are these guys right here. So use the following information to answer the next 5 exercises. Javier volunteers in community events each month. He does not do more than 5 events in a month. He attends exactly 5, 35% of the time, 4, 25% of the time, 3, 20% of the time, 2, 10% of the time, 1, 5% of the time, and 0, 5% of the time. So they want us to start by defining the random variable x. I don't want to do that. I want to start by making a table. Tables are great, and we'll summarize this nicely. So that's what we're going to do. So let's make this black and say that we've got number of events. So I'm going to call it like this, number events. And then probability or percentage. Now I think what they might want you to do is something like this. X, P of X. Right, so you can consider this, so X is the number of events attended, and the probability of that happening is P of X. So you can do it that way too if you would like. So he does, they list it in the order 5, 4, 3, 2, 1, 0, which is a weird order to list that in. I'm going to do it in 0, 1, 2, 3, 4, 5 order. And if I remember right, this was 5%. And again, I'm not going to write the percentages here. I'm just going to 5, 10, 15. Is that what it was? Did they just count up? 10, 20. They didn't. 20, 25, 35. 20, 25, and 35. And those, of course, are percentages. Let's see if that adds up to 100. So we've got 60, 80, 90. Yeah, okay, so we're good there. So they want me to define X, or define what X is, and I will say that X is the number of events Javier attends in a month. That's what I'm thinking X should be. What values does X take on? X takes on the, oh, I'm sorry, I should probably switch back here to this, define random variable X. So my definition, I assume they mean in words, but my definition is the number of events Javier attends in a randomly selected month. What values does X take on? 0, 1, 2, 3, 4, or 5. Construct a PDF, did that. Find the probability that Javier volunteers for less than 3 events each month. We can't do that. We can do in a month. That's poor phrasing. They mean in a randomly selected month. Find the probability that he volunteers for less than 3 events in a randomly selected month rather than in each month. So that's so in other words, probability of X is, say, less than 3, so X less than 3. So we can just get that from the table, or we could also just look from there. But X less than 3, that's 0, 1, and 2, so it's 20%. So those guys added up. Last one, find the probability that Javier volunteers for at least 1 event each month. Probability that X is greater than 0. Now, this one is easiest to do by the complement rule, right? So the probability that he does at least 1 event is all of these here, which we could add up 5 plus 10 plus 20 plus 25 plus 35, but we know what it's going to come out to be because there's only 5% of the time that he does 0, so this must add up to 95%. So there you go. I prefer to think of that as 1 minus the probability of 0. So 95% for that guy. All right, next problems were 23 through 27, I want to say. Where are we at here? Oh, come on, computer. Yeah, 23 through 27. All right, to find the random. Okay, so use the table to do the next 5 exercises. Physics professor wants to know what % of physics majors will spend the next several years doing postgraduate research. Is the following probability distribution. What's X? To find the random variable X. Good question. I'm going to assume that this is the number of years. That's what it looks like. Yeah, I'm gonna guess that's what X is. It's not clear from the statement here. A statement of the problem here at all. That's poor writing. I might have to assign a different problem there. Sorry about that. And it wants to fill in the table here. I'm gonna make this a little bit bigger so we can actually see this. Oh my God, PDFs. They're so bad about scaling. Come on, window, you can do it. I don't know if you can see this on the video or not, but it's scaling incredibly slowly. Okay. All right. So define the random variable X. My definition is that X is the number of years that a randomly selected graduate student will spend doing postgraduate research. So that's right. Yeah. Number of years. So I think X is the number of years a randomly selected postgraduate researcher will spend doing postgrad research. Define P of X, or the probability of X. Define it. The proportion of students, or the proportion of postgrads who spend that many years. So if X is 1, then and P of X is 35%, then I interpret that to mean that 35% of all physics grad students will do 1 year of postgraduate research, and that 20% will do 2 years of postgraduate research. Okay, we're going to need to fill in 4 here, so we need to add this up. So 35 and 20 is 55, and 15 is 70, 80, 85, so this must be 15%. So let's go ahead and put that in. So this is 15, 0.15. All righty. Find the probability that a physics major will do postgraduate research for 4 years, 15%. Find the capitalized I. Find the probability that a physics major will do postgraduate research for at most 3 years, so 3 or less. So that's these guys. So that would be 70%. Just add those up. On average, how many years would you expect a physics major to spend doing postgraduate research? Well, we're going to need expected value for that. So for that, I'm going to go break out my calculator. And then we're going to put X into L1, P of X into L2, and then we are going to do one variable stats with a frequency column. So calculator, where is that? I foolishly allowed, all right, hang on, mouse back. I foolishly allowed my PDF to take over my to full screen on my computer, which never goes well. All right, so let's switch over to the calculator. All right, calculator. Still got the calculations from the last homework on there. So I'm going to go to stat, edit. Actually, this is from the last homework. So I'm going to quit out of here and go to memory, clear all lists, which is number 4, and then go back to stat and edit. So they're all cleared up. Then I'm going to type the number of years. So X, 1, 2, 3, 4, 5, 6 into L1, and type probabilities. 35, 0.2, 0.15, 0.15, 0.1, 0.05 into here, and then we're going to find the mean of that. So the mean is expected value, so we're just going to do mean of that with a frequency column of L2. So I'm going to go to stat, calc, one variable stats, frequency list of L2. So what it's going to do is it's going to multiply 1 times 0.35 plus 2 times 0.2 plus 3 times 0.15, etc. It's going to, and then it's going to add all those up for us and put it in average. So 2.6 years. There's your average is 2.6. All right, so that's the expected value there. And by the way, I should let me pop back here for a second and zoom to some reasonable scale. Whenever you see the word expect, you should be thinking expected value. Very very clear tip off. If they say expect, you just think expected value. All right, so I don't know what the next problem is. The next problem is 69. All right. There we go. Suppose the PDF for the number of years it takes to earn a Bachelor of Science degree is given in table 4.31. All right, those are all decimal by 5, so this is clearly made up. In words, define the random variable x. X is the number of years that it takes to earn a Bachelor of Science degree. That's what they said here. What does it mean that the values 0, 1, and 2 are not included for x in the PDF? That it is not possible to earn a Bachelor of Science degree in 0, 1, or 2 years, which is probably not true. I bet you could do it. I bet a really dedicated student with a bunch of AP credits could probably do it in 2 years or less. But that's what it means. Like if they don't include it in the PDF, it means the probability is 0 for those amounts of time. All right, 70. Theater holds a fundraiser, sells 100 raffle tickets for $5 a piece. Suppose you purchase 4 tickets rather than 1, all right. Prize is 2 passes to a Broadway show worth a total of $150. All right, so a couple things. Number 1, we're not purchasing 1 ticket, we're purchasing 4 tickets, so I'm gonna make my PDF based on that. And the prize is 2 passes to a Broadway show. The fact that it is 2 passes is 100% irrelevant. You only care that the worth is $150. They could say, you know, the prize is a calculator worth $150, or the prize is a nice dinner worth $150, right? The fact that it's 2 passes is 100% irrelevant. So don't worry about the 2 here. That doesn't matter. You only care about the value. So 100 raffle tickets, we need that. $5 a piece, we need that. Purchase 4 tickets. And so it's going to be worth a total of $150. So what are you interested in here? It's a good question, book. I'm not totally sure. You didn't tell me what I should be interested in. I assume that the thing I am interested in is some combination of my probability of winning and the expected value of winning. But who knows? So I'm guessing that that's what they want me to be interested in. Find the random variable x. So x is going to be the total net winnings or losing. So total net profit that you get from purchasing 4 tickets. List the values that x may take on. Well, we're going to spend $20, so it could be -20, or we could win and get 150. So it could also be 130. So my choices are -20 and 130, because we have to take into account the fact that we're buying the tickets, right? So we're down $20 guaranteed. We might win the tickets or we might not, but we're down 20 regardless, right? So it's either -20 just total, or it's 130 total, right? Because we're up 150 but down 20. Construct a PDF. That's the thing I really want to do. So let's get a whiteboard going here. So make a PDF. So we're going to have x, p of x. So x is my total winnings. So we could win $130, right? Net, of course, or we could win, quote unquote, win -$20. And the probability of those things happening, well, there were 100 tickets sold. So the probability of us winning if we buy 4 of them is 4 out of 100. And of us losing is -96. 96. Sorry, I was looking at the negative sign there. 96 out of 100 is the probability of us getting -$20. So much more likely. So that's my PDF. That's all there is to it. List all the outcomes here and the probabilities of those outcomes. The book calls this a probability density function. I think I just called it in the video probability distribution. Same thing. If this fundraiser is repeated often and you always purchase 4 tickets, what would be your expected average winnings per raffle? That's not a good way to say that. So they want the expected value. That's what they want. So my expected value is pretty straightforward. It's just the way we calculate expected value is, where am I at here? Well, the way we calculate expected value is x times p of x, and then you sum it all up, right? So it's going to be 130 times 4 out of 100 plus -20 times 96 out of 100. And we could certainly do that in the calculator. In fact, let's do that in the calculator just because I want to do it the way that that I want you to get used to doing it. So yeah, we're going to do the same thing we just did here in this previous problem when we calculated expected value. I'm going to make a list of the outcomes. So the outcomes were 130 or -20, -20, And the probabilities of those were 4 out of 100, so 0.04, or 96 out of 100, like that. And so my expected value is just the average, right? And so I'm just going to use one variable stats, a list of L3. That's the thing I'm averaging. Hello, click L3, frequency list of L4. Average, as we would expect, is negative 14, is negative, right? So we're expecting to lose $14 on average of our 20, right? So that's the long-term average there is $14 lost per time we do this raffle if we buy 4 tickets every time, which should be 100% expected, right? Like you should expect to lose money, or the expected value has to be negative in any raffle you do, because from the consumer's perspective, you're well, from the person who's running the perspective of the person who's running the raffle, they have to take in more money in tickets than they put out in prizes, or else they're not going to gain money doing it. And so that means that their positive money is your negative money, is the consumer's negative money, which is, that's the way it's the way it goes with raffles. You can also tell this, by the way, here, I'll just have a quick aside here. You can also tell this just by looking at the totals, right? 100 raffle tickets for $5 a piece means they take in 500 and put out 150. So they are $350 up, assuming they actually sell 100 tickets. So that means that if you take that, so that means that they're negative 350 or negative 3, excuse me. From the consumer's perspective, the total amount the consumers lose is $350 among 100 people. If we divide that by the number of tickets, we get $3.50 per ticket. That means that we're expecting to lose negative 350 per ticket. We bought 4 tickets. 4 times negative 350 is negative 14. So you can do it that way too. All right, what was the next problem? 75. Oh yeah, 75 I like, because it is interesting to think about what it means for riskiest. All right, so a venture capitalist willing to invest $1 million has 3 investments to choose from. The first one, a software company, has a 10% chance of returning $5 million, 30% chance of returning $1 million, and 60% chance of losing the $1 million. Second company has 20% chance of returning $3 million, 40% chance of returning $1 million profit, 40% chance of losing the million. Third company, biotech firms, 10% chance of returning $6 million profit, 70% chance of zero, and 20% chance of losing the $1 million. So this is, so firstly, for those of you interested in going into business, there's no point at which you can actually assign percentages to things like this. Don't be deceived by that. This is just if we knew all the outcomes, here are the actual percentages. So this calculation is not a thing you really do in business, sort of. Expected value is really important, and you might sort of empirically assign percentages like this. But this isn't like a realistic choice to make here. Anyway, construct a PDF for each investment. All right, so the nice thing is they're telling us this in terms of profit, right? Not net. So the $1 million that we invest, once we invest it, it's gone, right? Now, it buys us a stake in these companies, right? So if we invest $1 million, we get, it says $5 million profit. So that means that we made $6 million back, right? And then minus the $1 million that we invested. So this is the way they're phrasing this is essentially the same thing as a raffle, right? You got 3 different raffles. A ticket costs $1 million. First one has a first prize of $5 million, a second prize of $1 million, and a third prize of nothing, right? That's essentially what we're doing here. So let's go ahead and make the PDFs. Let's get the whiteboard going. We can do a page. So we got investment 1, NV1, INV2, and INV3, and V3. So XP of X, where X is profit. That made those too close. And I'm going to do everything in denominations of $1 million since everything is given in denominations of $1 million. So the first one, we could have $5 million profit, a $1 million profit, or lose $1 million. And the probabilities of that were something I don't remember. +5, so it's 10% to get +5, 30% to get +1, and 60% to get -1. So 10, 30, and 60. This doesn't look like a great investment. So we had 0.1, 0.3, or 0.6. The second investment, the hardware company, I see they mean computer hardware, but maybe they don't. Maybe they just mean like nails and hammers kind of thing. 30% to get, wait, where are we at here? 20% to get to be +3, 40% to get +1, and 40% to lose everything. So we got 3, 1, -1, and it is 20, 40, 40. Yeah. So we get 3, 1, -1. This is 0.2, 0.4, and 0.4. And then the third company, the biotech firm, yeah, 10% chance. So we got 10, 70, and 20. So we got 6, 0, -1. All right, so still positive investment, but so we got 6, 0, and -1. That was 10%, 0.7, and 0.2, I believe. Okay, so there we go. Make sure I got that right. I think that's right. Find the expected value for each investment. Okay. So certainly you could type this all into your calculator and that would work just fine. I'm gonna probably just do this in my head. This is gonna be 0.5 plus 0.3 is 0.8 minus 0.6 is 0.2. So we got mu of x equals 0.2. So in other words, on average, it's plus 200,000. This one's 0.6 plus 0.4 is 1 minus 0.4 is 0.6. So this is mu of x equals 0.6. And this guy is 0.6 plus 0 minus 0.2 is 0.4. So mu of x is 0.4. Again, in millions. So this 0.4 is actually $400,000. So these are all positive, right? So this guy is very likely to make money, or on average will make money. It's actually not that likely that they'll make much money, that they'll make money if they invest in investment 3, right? It's only 10% chance, right? There's a 60% chance that they'll make some money on investment 2 and a 40% chance they'll make some money on investment 1. And so this gets to the riskiest versus safest question, which was which is the safest investment? Why do you think so? So I don't like the way they ask this, why do you think so? Because the question depends entirely on your definition of safe, right? So one definition of safe is probability of gaining money. That's certainly that's probably what they're going for here. However, depending on what type of investor you are, you might define safest in a different way. Like for instance, let's say you work for a venture capital, or not that you work for a venture capital firm, but let's say this, so they have a venture capitalist here. Let's say that this venture capitalist is not just out on their own. They're not just like a one-person entrepreneur, that they are someone who is scouting investments for a larger company, right? So for a hedge fund. Then safe might mean the one that is most likely to get me promoted, right? And maybe to get promoted, you need to have a big return on your investments. So safe might mean something different to that. Risky is just the opposite of safe here, right? So, which is the riskiest investment? You could define that in a variety of ways as well. So I'm going to define safest as most likely to return a profit and riskiest as most likely to cause a loss. In which case, we just look at the total probabilities in each case. So the probability of investment 1 returning a profit is 40%, investment 2 60%, investment 3 10%. Right. So for me, I think that investment 2 is the safest investment. Now, they did this in a not very interesting way, where the safest investment also had the highest expected return, which is, sure, if you want to define safest in terms of expected return, you could do it that way too, right? If you have like a lot of investments, then and you're aggregating them all together to mitigate the risk of each one, like you get to average the risk over all the investments basically. Then you might just want the highest expected return, right? That literally might be the thing that you want, and to you, that might be the safest, even if it doesn't necessarily have the highest probability of making a positive return. You might still prefer to just have the highest expected value if you have a lot of these investments and you can afford the loss. So yeah, depending on how you define safe or risky, there you go. I define safe as most likely to return a profit and risky as most likely to cause a loss. You could also say that safe is most likely to not cause a loss and risky is most likely to cause a loss, in which case the safest investment would be investment 3, right? 80% of no loss, 80% chance of no loss, but only a 10% chance of an actual profit. So just depends on how you define your terms here. So just the lesson I want to get across here, and why I assigned some extra credit points for discussing thoughtfully risky versus safe, is that how you define your terms basically determines everything. So define your terms really clearly, know what you mean by risky and safe, and state it. Like, you just come right out and say exactly what you mean, so that other people who are following what you're doing can, agree or disagree with you and make their own calculations based on that. But it tells them why you reach the conclusions that you reach. So define your terms clearly, very important. Riskiest, which one most likely is, to me, this means which one is most likely to cause a loss, which is investment 1. Investment 1 has a 60% chance of losing the $1 million. So to me, that's the riskiest one. You could think of risky as most likely to not return a profit, in which case investment 3 is the riskiest, right? 90% chance of no profit. But if losing money is what you consider risky, then the first one has the riskiest investment. Which investment has the highest expected return on average? It was investment 2. It had expected value of plus 600,000, right? So expected value plus 400,000 here and expected value plus 200,000 there. Pardon me. Sorry, getting a message that my video is done encoding. Yeah, this is 0.4 million, 0.6 million, 0.2 million. So there you go. All right, let's look at the next problem. So what is the next problem? Next problem is number 92. 92. Page down, away that there. 92. Student takes a 10-question true-false quiz, but did not study and randomly guesses each answer. Find the probability that the student passes the quiz with a grade of at least 70% of the questions correct. So this is a binomial question. This question is about the binomial distribution. You can tell it's binomial because it meets all the Bernoulli requirements, right? There are only 2 outcomes, either right or wrong on each question. There are a fixed number of trials, so there are 10 questions on the test, and then each one is a separate trial. There's a fixed probability of success each time of 50% right, 50% wrong, so 50% success, 50% failure. And the thing that we are counting is the number of successes, right? So you have to meet all those Bernoulli requirements for geometric as well. But you're counting something different. And in the geometric case, you're counting the number of tries till the first success, which is, I think, the next problem. But in binomial, you're counting the total number of successes in a fixed number of trials. So that is, we're looking for a total number of successes in 10 trials. And they want to find the probability the student passes the quiz with a grade of at least 70% of the questions correct. So I want to go to whiteboard and just, oh, did I never ever switch back to that? I don't remember if I ever switched back, sorry. So it's what we were looking at 92 here, right? This guy. That was the thing I was just describing. Feel free to pause the video and read that if you need to. All right, so there are 0 through 10 possibilities, right? You could this person get 0 questions right, or 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9, or could get all 10 of them right, although it's quite unlikely. The ones they asked about was, what's the probability of getting at least 7 right? What's the probability of passing a test with at least 70%? So we are interested in this. Now, I'm going to use the binomial PDF in the calculator. Oh, excuse me, I'm going to use binomial CDF, my bad. And the reason I'm going to use binomial CDF is because I am asking about this, right? The question asks, what is, if X is the number of questions right, what's the probability that X is greater than or equal to 7? And the only time you use PDF is if this is just exactly equal, but we have greater than or equal to. So what I want to do is 1 minus PDF of 6, because the ones that, so your calculator only does less than or equal to, right? That's what PDF, or that's what CDF does, is less than or equal to. So what I want to do is notice that I want to not include this. I want to not include 0 through 6. So I'm going to do 1 minus PDF of 6, or 1 minus CDF of 6, excuse me, I said that wrong again. So this is 1 minus the probability that X is less than or equal to 6, right? And so that's what we're going to do, because the calculator does CDF. When it does CDF, it does less than or equal to. So let's switch over to the calculator. So we're going to do distributions. Yeah, that's fine. Binomial CDF. So the number of trials, we had 10 questions, probability of success 0.5, and we are looking for 6, 6 or less, right? So that's the probability that the person will get 6 or less right. So 1 minus the answer is the probability they'll get 7 or more right. So it's pretty unlikely, right? The expected outcome here is to get 5 right and 5 wrong, but even just 2 more than that is quite unlikely. Right? Just only 17% to get 7 or more right. So there you go. It's 92. What's the next question? Next question is 105. So let's go look at 105. Oh, come on. It's so finicky. So finicky about going where I want it to. 105. Suppose the probability that an adult in America will watch the Super Bowl is 40%. And they say each person is considered independent. I hate how they say that. That's almost certainly not true, but we're just gonna roll with that. We are interested in the number of adults in America we must survey until we find one who will watch the Super Bowl. So I presume what we're gonna do is dial a random phone number and ask the person, hey, you gonna watch the Super Bowl? So that we get people from, different walks of life and different parts of the country, right? Like I bet you people in the South are much more likely to watch the Super Bowl than people in the Northeast. And it's going to depend on like what city, which teams made it. If it was Kansas City and Tampa Bay, and we call up somebody in Missouri, they're probably watching. If we call up somebody in Montana, there's a good chance they're not. So that's why I don't like the independent bit, but there you go. Probably depends on the region we call. Anyway, we're just going to assume that they're all independent. So the thing you want to notice here is that we are we meet Bernoulli trials. We meet the Bernoulli trial requirements. There's only 2 options. Success is they will watch the Super Bowl. Failure is they will not watch the Super Bowl. There's a fixed probability of success, 40% success, 60% failure. Each trial is independent because they say so. Each person is considered independent. And then, so that's what you need for Bernoulli trials. And then the thing that we're counting is the number of people we have to survey until we find one who will watch the Super Bowl. So in other words, how many people do we have to ask until we get our first success? So that's how you can tell it's geometric. Okay, in words, define the random variable x. I presume x is the number of people we have to call, so we are interested in, why is it doing the hand thing? We're interested in the number of, come on. Survey until we find one who will watch the Super Bowl. They literally tell us what we're interested in. So that's x. X is the number of adults in America we must survey until we find one who will watch the Super Bowl. List the values that x may take on. It could be a lot, right? It could be 1 or possibly 2 or 3 or 4, or we could get super unlucky and call literally everyone in America who's not watching the Super Bowl before we hit the first person who is. So that would be some large number of people. There are 200 million-ish adults, maybe 220 million adults in America, something like that. So we could call 60% of 220 million adults. So you can't list all those. You know, so the list the values of x, list the values that x may take on should be something that looks like something that looks like this. Right. So B, you'd want to have like 0. Oh, I suppose I should make these curly braces, pardon me. Curly brace. 0, 1, 2, ... However many people. In the US won't watch the Super Bowl. Right. You could pick a number for that. If you just put 0, 1, 2, comma, ... and then ended it there, I would accept that as well. Like it doesn't technically go up to infinity, but the number is so large that treating it like it goes on forever is fine in this case. Give the distribution of x. X is approximately, oh, this is terrible. It's not that at all. They've left 2 things in here. I presume because they copy pasted this from binomial. But there's only one parameter for geometric. So this is geometric with a chance of success of 0.4, 0.4. That's it. There's not a second number in there. I don't know why they left 2 spaces. Sorry. How many adults in America do you expect to survey until you find one who will watch the Super Bowl? So they're asking for the expected value of the geometric or expected value of this distribution. So the expected value of a geometric distribution is 1 over the probability, 1 over probability of success, so 1 divided by 0.4, which if you do that in your calculator, you'll find is 2.5. So I'm expecting to have to survey, on average, 2.5 people before we find one who watches the Super Bowl. Find the probability that you must ask 7 people. So we're going to go ahead and use geometric PDF. So probability that you must ask 7 people. That's 7, so exactly 7 people. So the probability that x equals 7. So here we use PDF because it's equals. So I'm going to go to the calculator. We're going to go geometric PDF. Geom PDF, I think is what they call it. Oh no, shoot, I messed that up. Geomet PDF. Probability of success is 0.4. We're interested in knowing probability of asking at least 7. 1.86%. There you go. And then the last part is find the probability that you must ask 3 or 4 people. There's a couple ways you could do that. I think it's probably easiest to do PDF of 3 plus PDF of 4. I think that's the simplest one, so that's what I'll do. Geometric PDF of 3 plus geometric PDF of 4. You can do these one at a time if you want, or find them separately and then add it up if you want to. I'm not going to bother, I'll just do that. So 23.04% is the answer to F. Last problem, I think. Yeah, last one is 118. I believe that's the maternity ward one, right? A lot of people have trouble with this one. Yeah, maternity ward at Dr. Jose Fabella Memorial Hospital in Manila in the Philippines is one of the busiest in the world. That is not a surprise. The Philippines have a lot of people with an average of 60 births per day. That is a lot. That is a lot. Think about 60 babies being born in one hospital ward in a day. So let X be the number of births in an hour, not in a day, but in an hour. So here we're looking at Poisson, right? So this is number. It is a number of things in a fixed time and or space. Number of occurrences. So occurrences are births, and the fixed time and or space is the maternity ward at Dr. Jose Fabella Memorial Hospital, and the time is an hour. So find the mean and standard deviation of X. Well, we're going to need to quickly define what X or what we're using here. And so this is a Poisson distribution with a lambda of 60 over 24, right? So lambda is the average number of occurrences of the event in the unit of time that you're looking at. So if there's 60 births a day, then there's, and we're looking at an hour, that gives us an average of 60 divided by 24 per hour. Find the mean and standard deviation. All right, so you want to use the mean and standard deviation formulas. Well, mean is literally lambda, right? Lambda is mu. They're the same thing in a Poisson. So 60 over 24 is mu. So that's what, 2.5? Yeah, 2.5 is mu. Standard deviation for Poisson is the same thing as the mean. This is of course not a general rule for every distribution, but in Poisson, standard deviation and mean are the same. So 2.5 as well. Sketch a graph of the probability distribution of X. So you can make a histogram of this if you want to. So let's go to here. Let's go to whiteboard. Get a new one. So this is not a thing you can actually make a probability distribution of because it goes on forever, right? So we could have X, P of X. So we could have no births in a given hour, or 1 or 2 or 3. And there's no theoretical upper limit of this. Obviously, there are some practical ones. But so here what we have is, this is Poisson of lambda. Oop. This is Poisson of 2.5. And so what we can do is we can find probability that X equals 0 and put that here. And the probability that X equals 1 and put that there. Probability that X equals 2 and put that here. And we could do that for each of them, but I want to batch process it, right? I want to do a whole bunch of them at once. And your calculator is great at that. So lists are going to be useful for this. So you certainly could do these one at a time. And what you would want to do here, we'll just do the first one. I'll do Poisson of 0, just so you can see what it would look like if you want to do them one at a time. I would go to distributions, Poisson PDF. Mu is 2.5, so mu is lambda. On your calculator, it probably has a lambda here if you're using a physical version of the calculator. Later on, they updated it so it uses mu here, which I don't think they should have done because most people call this lambda. X value is 0. So probability of getting 0 births in a given hour is about 8%, 8.2%, like 0.82. So I'll call that 8.2%. So let's go put that over here. 0.082. And then I could do the same thing for 1 and for 2 and for 3 and for 4, et cetera, et cetera. And I don't want to do that because let's say I'm going to go to 10, let's just say. You certainly don't have to do that many, but I will just to show you that it's relatively easy. There's a couple ways you could do this. The simplest one is to go to lists, and I think I have a bunch of stuff in here. Yeah, I do. I'm going to go ahead and remove all this stuff. We're going to go to memory, clear all lists, and go back here. Everything's gone. And so what I could do is I could do 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then in L2, I'm going to go into the header of L2 and do Poisson PDF of L1. And it'll give me all the probabilities there, which is really convenient. Makes for a nice table. So if I go to what is that? Distributions, Poisson PDF of 2.5, X value is L1, second L1. Right, so there we go, we're at Poisson PDF of L1, and it gives me all of them. Very convenient, right? Super nice. One nice thing about this is that we can make a histogram out of this. We should be able to. We make histograms. So your calculator will make histograms. I don't know if you knew that, but I'm going to make L1 or plot 1 here a histogram like that. X list L1. No, that's no good. That doesn't work. I'm going to have to make a scatter plot out of it. So the X's are going to be in L1 and the Y's are going to be in L2. So the X's are the number of babies born, and Y is the probability of having that happen. So yeah, we should be able to do it like this and turn plot 1 on. So let's go make sure I don't have anything else on. Yeah, I don't have anything else on. So plot 1, and then we're going to graph it. This obviously doesn't do a very good job of displaying it, so we're going to zoom stats. So zoom number 9. There we go. There is my quote unquote histogram. Right, so you can see probability of 0 is 8%. Oh, here, let's trace. Probability of 0 is 8%. Probability of 1 is 20.5%. Probability of 2, 25.6%. Probability of 3, 21.3%, et cetera, et cetera, et cetera. Right, shows up to 10 because I did 10. You can do as many or as few of these as you want. I mean, make it a reasonable number, right? Do like maybe 6 or 7, something like that, just to get a good sense of the shape. But there you go. That's what my probability distribution looks like. Yeah. Another thing that you can do is this. You could do you could go to y equals. I'm going to turn this off and do in my y1 function. I can do Poisson PDF of x, and I'll show you where you can go with this. So Poisson PDF of x, and paste that in there. And then if I go to make a table, it'll give me all the possible x's. Right, it'll keep going forever. It doesn't list the probabilities for less than 0, of course, because it's not possible to get less than 0 births in an hour. And you can do it that way as well to find all the probabilities quickly. So I would do the lists. I like lists better. I like doing something like this because it lets you treat this like data, right? You can make a graph of this really conveniently. But you could do it a different way as well. Anyway, let's go back to the problem. Sketch graph. We did that on the calculator. What's the probability that the maternity ward will deliver 3 babies in 1 hour? Well, we can just go look. 3 babies, 21.38%. What's the probability that the maternity ward will deliver at most 3 babies in 1 hour? So 0 or 1 or 2 or 3. So I'm not going to do this one all the way out, but you would just add up the probabilities here. Probability of 0.0821 plus 0.2052, etc., up to here. Whatever that is the answer. It's like probably 70-ish something percent. What's the probability that the maternity ward will deliver more than 5 babies in 1 hour? So this one is a little bit tricky because there's no upper limit for this. Right? So there's more than 5, so 6 or more. So just adding up these is not enough because it could, like I didn't include 11 or 12 or 13 or 14. The probabilities of those are small, but not 0. So what you really want to do is 1 minus the probability of 5, right? So they're asking about more than 5, so 6 or more. So what you want to do is 1 minus the probability of 5 or less. So 1 minus Poisson CDF of 5. So might as well find that, right? Put out of here, distributions. I forgot to do the 1 minus, but that's fine. So I want 1 minus this. So 1 minus that number, so it looks like 4.21%. Yeah, 4.2%. And there you go. All right, I believe that was the last one on the homework. Is that correct? Yes, that's correct. All right, so there, that is the last problem on the homework. So I'll go ahead and stop the video there. All right, I will see you guys in the next video.